Yeah, thank you very much. My name is Xiangyu from Technical University of Munich. Today I would like to present a work on this SPHinXsys, which is a code we are developing on this parallelization with SYCL or SYCL. I'm not sure which one should be the right way to pronounce. So the outline of my talk is like this. I would like first introduce slightly SPHinXsys and smooth particle hydrodynamics, which is a method which was used in this library. And I also would like to introduce briefly GPU accelerations for SPH-based code and SYCL or SYCL. And then I would like to give more details on how existing parallel methods adapt this our method adapt to the executable with SYCL, this code, this paradigm. And we will introduce this parallel execution policies, how the memory model and execution model, and how do we do the data sorting for this for this particle method which are using. Then I would like to show some benchmarks to compare the SYCL parallelization and the original multi-core CPU implementation performance. After that, I'll give brief conclusion and outlook. This page is a little bit special. So the SPHinXsys is a multi-physics library, and it's a C++ code API for physical accurate simulation and optimization. So the parallelization we are using is not very new, is the Intel's TVB library, which the special part of the SPHinXsys is a coupled industrial dynamic. He simulates a coupled industrial dynamic system. So that means the fluid, solid, the multi-body dynamics and more, they are all coupled by a unique and unified computational framework based on the SPH method. So the strong coupling is used for all involved physics, and the approach itself is monolithic because it's based on one numerical method for all physics equations. And with this, as is a library, so with this library can do a straightforward and fast prototype modeling of body physics. Even this method is a particle approach, but they can be still fully compatible to classical finite volume method. Basically, they can be used to implement exactly the same code. And also the code itself have a target-driven optimization. It's embedded inside the SPH algorithm, and also with Python interface, which used for regression tests, the continuous integration, and the machine learning. For example, we use reinforcement learning and the Python interface to train dynamic systems. Okay, that's the basic information of SPHinXsys. So as we use a monolithic approach for all physics, so the method we choose is so-called smooth particle hydrodynamics. This method, they use particles provide a discretization approach, so it's a point-based entities. And this method itself is very similar finite volume approach for general CFD. The only difference is the particle method without using a mesh. And if you look at the computational algorithm, the particle method is almost same as molecular dynamics. So because they are searching, neighboring, and sorting, they are all basically the same thing. So difference is SPH solving dynamic system of continuum media, not like molecular dynamics directly solve the microscopic system. And so one important thing of this SPH dynamics is they use neighborhood with a cutoff radius like molecular dynamics to introduce interaction between the particles. So compared to the traditional mass-based approach, so use this neighborhood relation where this will be very convenient to track the interface, to detect the multi-body interactions, So because they are very flexible without the prescribed geometry or topology, so that make this particle methods much more flexible than the classic approach. But the introduced particle and the neighborhood also introduce more computational effort, so that we really require high performance computing for these simulations. And so SPH is not new method, so many people already implement SPH libraries with GPU support. For example, they have a dual physics and Pi SPH and Aqua as GPU SPH. They all already have this GPU accelerators implemented, but usually they use this like CUDA or OpenCL standard, which more like low-level approach. So the motivation of the present work is we would like to enable in the already existed SPHinXsys library so that it can execute on heterogeneous hardware, including GPUs and CPU together. And we would like to use the SYCL standard for parallel computing. That's because SYCL is a good option for us, I think, because they are close cross-platform abstract layer and offer really the standard C++ interface. We don't need to learn hardware-related things, and so that's easy to achieve parallelization for different hardwares, and the same code is compiled for both CPU and the accelerators. So they make this implementation more concise and easily maintained. So the SYCL mode we are try to use is basically use the SYCL computational kernels, and which is a block of code which would like to execute on the target device, and we identify the difference between the host and the device. By host, they will introduce the code queue or the command group to control this computing, and the computer itself is executed on a GPU or CPU at the same time. Both okay, because this is a very good property, because if you have a public repository platform like GitHub, you don't have GPU for the continuous test, but if you use a SYCL, you can still test your code, because you can simply switch the GPU to CPU, then you test your GPU code there. So the standard CI workflow can also works. So SYCL uses some special memory mode to make this memory arrangement simpler. So the original one is so-called buffer mode, which is a mimic the buffer used in the CPU computing. But recently they introduced more on this unified shell memory, so that we can allocate memory directly, but by specify accessibility for host or device. So, and we can also use a row pointer as very old-fashioned of C in this SYCL code. So, and also good for this unified memory is you can, if memory is only used by device, you only need to locate this memory on device, then never accessed by the host. So to do this, we would like to have a look first at what the typical flow simulation in SPHinXsys, so that we can cope with this by parallelize this code. And for a typical simulation particle method, we use fluid and structures. We are all defined by particles, and the particles interact with its neighbors within the cutoff radius. And for these neighbors, we need so-called cell-linked list searching algorithm for the neighbors. So for this current, this SPHinXsys, we already have this heterogeneous parallelization by using so-called particle iterators. We basically have two iterators functions. One is called particle for loop, and the particle reduce for reduce operations. And we decided which one to, for example, sequential or parallel by so-called execution policy, which decided by at the compiling time. And based on this, we can introduce parallelization with SYCL by introduce SYCL execution policy as a new policy beyond the old policies. So basically, this also using the template specification determined at the compiling time, just introduce two more policy for this particle fall and the particle reduce. But this is not so trivial because for GPU they use different way to manage memory. So we need have a special way to make the data management. Basically, to achieve the device copyable data, we will use unified shared memory and the row pointers for this memory location. And the original cell link list code would be based on the STD vector. So though now they are not able to use STD vectors anymore, so we need to use the traditional approach, the head list or cell list to approach this. For parallelization, we need to introduce atomic operations. And for GPU, for CPU, before we save the particle neighbors when we do the calculation, but this would be very expensive for memory because for GPU the memory is not much, so we need to use a direct search without saving any neighbors. So this is more efficient for GPU. And the other things we need also introduce a different sorting approach because for Intel TBB, they have their own sorting, but they're not able to use in GPU. So we need to introduce so-called radix sorting, sorting for the index, and after sorting the index, we need to move all the particle data which need to be sorted. So here is a typical example of this code. We first define the policy and we define or initialize all the computing kernels. And we run the computing kernels, and during the running, we can introduce so-called event-driven output to hide a little bit communication time between GPU and the CPU. So that's basically the example of this. After implementing this, we can have a test. So the test is not compared with single CPU; is compared with the multi-cores. Computers, CPUs. So that means we compare with all the one mode with all CPUs and one mode with only one GPUs. So here, this tool is for 2D and 3D simulation with increasing number of particles. So this bottom line is the fastest one with direct search with SYCL, and the slowest one in 2D is the TBB with double flow point calculation. But for 3D, it's similar, but in this case, for direct search, if you use double on GPU, you can get much not very good results. So it looks like if you use direct search and you got much higher acceleration, and if you use double, then have difficulties. This is one computer like 12 cores for CPU and one old NVIDIA card. And for new architecture with more advanced CPU and more advanced card, you got a very similar performance. Basically, you got about 10 times of accelerations. But here is different because this AMD card is here is 64 cores. So that means in this case the GPU is much more powerful than before. So but basically you still see about 10 times of performance increase. So that's the general overall performance after you introduce SYCL. And now we would like to see some details. Yeah, almost finished. Some details of this, and for example, you can compare with the simulations and compare with two different devices. And one is new GPU card, and you can see the new card is much faster. And also, if you use direct search, don't save the configuration of particle neighbors, you got much less save of memory, about 10 times of less. So then you can simulate big computational problems. So here you see this is 2 million, that means you can do 10 times of this. This is 20 million. Okay, so that's, and last one I would like to show this sorting, because we can use the SYCL provide the sorting or by our own sorting, and we can compare with TBB for the CPU. Then as you can see, the GPU sorting is much faster, and with time with size goes on, you don't increase your sorting time too much, because you see the number of particles become very large, but the sorting time almost the same. Okay, so then I come to my conclusion. So basically, I feel that additional accelerator will be very good for particle simulation if you want to consider increase computational efficiency, and the SYCL would be quite good to use for heterogeneous system, and they were implement as extra execution policy or execution model is applied for a SPHinXsys library, and the performance shows that we got quite good performance, and without not much change of the original code, because what we do now is more like memory mode and execution policy one more, so that basically the minimum effort. So with this promising result, certainly we would like to have more methods in SPHinXsys to be progressed adaptive with SYCL. Currently only fluid dynamic simulation there, and solid and others we will also use SYCL. And also the source code is actually variable with the so-called SYCL branch in the original SPHinXsys main repository, and if you have interest, you can have a look. Like here, this SYCL branch of this code. Okay, thank you very much.